Hello everyone, I hope you're all doing well and you're all healthy. In today's lecture, we're going to cover section 5.3, the definite integral. Before we start talking about the definite integral, let me tell you this. Calculus is mainly about two notions, the notion of differentiation and the notion of integration. And what brings these notions together is known as the fundamental theorem of calculus. Okay, what ties these notions up is the fundamental theorem of calculus, which we're going to learn later. Now, these notions were not invented because Newton and Leibniz just got bored. They actually serve certain purposes, like they have geometric meaning. What was the geometric meaning of the notion of derivative? If the derivative of a function at a point exists, then that derivative is actually the slope of the tangent line of the graph of that function at that point. And what's the motivation behind integral? The motivation behind integral is basically finding areas of planar regions. So let me write the following down. So our motivation is this. How do we find the area? Okay, I'm going to first focus on finding the area of regions which are regions between the graph of a function and the x-axis over some interval. Okay, how do we find the area of of the region under y equals f of x over an interval AB? Okay, so I should explain what I mean by this. The region under y equals f x over AB. So let me draw a picture. Here, a prototypical picture that I'm going to use later. So let me draw a big one. Let this be my picture. Okay, so this is x, this is y, and over here I'm going to have my a, over here I'm going to have my b. And for now, I'm going to pretend that my function takes positive values. Okay, so I'm just going to put my graph. Just give me a second. I'm just going to draw my graph as if it's the case that my function is always positive, which is not necessarily the case, but I'm going to talk about what integral means when you have a function which can take negative values. For now, let's stick to this case. Okay, so let's take a function whose graph looks like this. So what we want to do is we want to find the area of this region. Okay, so when I say the region under y equals f of x over ab, what I mean is this. It's the region which is stuck between the curve y equals f of x, the curve y equals 0, the curve x equals b, the curve x equals a. I mean, these are lines actually. So our motivation is this. Like, how do I find the area of this region? Okay. So before like in the last video, we actually kind of learned what our approach should be. Remember, we derived the area formula for a disk. We proved that the area of a disk with radius r is pi r squared. And how did we do that? What we did was that, like, we took a disk and we approximated disk from within and from outside using a regular polygons, which are made of triangles whose areas we can actually compute. And then in that approximation process, we took the limits of the areas of polygons which are approximating from within, and we took the limit of areas of polygons which are approximating from outside, and those limits were the same, and we said that, okay, that should be the area of this disk. Okay, so we're going to do the exact same thing, except instead of triangles, we're going to now use rectangles. Okay, and here's what we're going to do. So I'm going to suppose that I have a continuous function here. Okay, let f be continuous over the interval AB. I'm gonna explain why I'm assuming this at the moment. So I'm supposed, like, as a starting point, I'm assuming that I have a continuous function on a closed and bounded interval like this AB. Okay, a a partition a given a partition now I need to define what a partition is. Maybe I should just write this in red so that you'll see that I'm making a definition. Given a partition, that is a partition of AB, that is, now what's the partition of AB? It's just a bunch of points in the interval AB where the first and the last points are A and B respectively. That is a set of points x0, well, let me start with 1, x1, x2, x3, Let's say that I have m points, xn with, now these points are pretend that they are ordered like this. X1 is less than x2, less than x3, and so on. I want A to be equal to x1, and x2 should be less than this, x3 should be less than this, and so on. And you go up to xn, and I want xn to be B. Okay, so this is my x1, and I have some point here x2, and I have some other point here x3, and I have some other point here, let's say x4, and let me also mark x5. And you have such points, and you go up to xn. Okay, so this is a partition. So a partition of AB is simply a bunch of points, two of which are A and B. And when you talk about partitions, it's common it's common practice to order them like this. Like if you name it x1, x2, xn, you're simply assuming that the first one is your the left-hand point of your interval, the last one is the right-hand point, and these guys are ordered. Okay, so given such a partition, we define the upper Riemann sum of f with respect to p. Okay, so I'm making a definition. I'm defining the upper Riemann sum of f with respect to p. The upper Riemann sum of f with respect to p will be the following. For each of these intervals, I'm going to find in the first interval x1, x2, I'm going to find the largest possible value of f, which is what? It's this. And I am going to create this rectangle, okay? I'm going to create this rectangle. And I'm going to do the exact same thing for each of these intervals, xi plus 1. So for the interval x2, x3, this is the largest value of f. So I'm going to create this rectangle. And let me do two more. The largest value of f is over here on this interval, so I have that, and the largest value of f is over here in this interval, so I have this. And let's say that this is like xm minus 1, and over here this is going to be the largest value, so I have this. So what I'm going to do is I'm going to create these rectangles, and I am going to add the areas of these rectangles up. Okay, and that will be called the upper Riemann sum. So upper Riemann sum, I'm going to show it by this notation UFP. So this is the upper Riemann sum of f with respect to the partition P. This is defined as the following. So I'm going to use the sigma notation. A sigma notation is section 5.1, which we skipped. So they used to teach this in high school. Maybe they don't teach it anymore. In any case, I'm not going to do a separate video for 5.1. Okay, that's your reading assignment. Go and read 5.1 if you don't know what sigma notation is. Okay, so I'm going to write this down in sigma notation. Here it is. It is the maximum value of f of x, where x is in this interval. X is in this interval. xi plus 1. Okay, and I'm going to multiply this with what I'm going to call delta xi. Okay, and I is going to change from 1 to n minus 1. Okay, so as I said, I wanted to add the areas of these three rectangles up. How do I do that? Like, I have n minus 1 rectangles here. Okay, and if you pick some arbitrary rectangle over here, let's say you pick a let's say that you pick this, pretend this is xi, this is xi plus 1, okay, and the maximum value of the function is over here, and this is your rectangle. What is the area of this rectangle? Okay, what's the area of this? The area of this rectangle is the height of this times the width of this. Remember in 5.2 when we talked about the notion of area, this was one of my assumptions. If I have a rectangle with sides A and B, the area of this rectangle is AB. So the area of this is this width times this height. But what is this height? Like, how would I construct this rectangle? The height of this rectangle is the largest possible value of this function over this interval. So over here, the term which I wrote over here, max of f of x, where x changes between xi and xi plus 1, this is the height of the rectangle of this rectangle. Okay, and what I'm calling here delta xi is simply xi plus 1 minus xi. So this is a xi plus, this is defined as, like, I'm defining this as xi plus 1 minus xi. So this is the width of the rectangle. So this product gives me the area of this rectangle, and I want to add these areas up as changes from 1 to n minus 1. So you plug in I equals 1, you compute this number. You plug in I equals 2, you compute this number, you get the area of this. You plug in I equals 3, you compute this number, you get the area of this. So you add these up, okay? And when you add these up, you get the upper Riemann sum of f with respect to this partition P. Okay. Now you may ask the following question: why does this maximum exist? Why does this maximum exist? This maximum exists because this exists because f is continuous on the interval xi plus 1. You see, I assume that f is continuous over the whole interval. So in particular, it's continuous over on this closed interval. Now, if you have a continuous function on a closed and bounded interval, remember the min-max theorem told us that there is a maximum value of the function, okay? So the maximum value of the function is attained. So this maximum actually exists. There is a point in this interval which makes this function attain its maximum value. So that this number actually exists is from the it follows from the assumption that f is continuous, okay, over this interval. This is why I assumed f to be continuous. Otherwise, I couldn't have written this down. Okay, so that's the upper Riemann sum, and you can guess how the definition is going to go for the lower Riemann sum. So we define blah blah as blah blah, and the lower Riemann sum of f with respect to p as, now you can guess what's going to happen. Instead of max, I'm going to write min. Okay, so L of fp, lower Riemann sum of f with respect to p, it is going to be, so I'm going to take the ith what I'm going to do this time is for each interval I'm going to find the point which makes this function take its minimum value. So for the first rectangle, it's over here. This is the minimum value of the function over here. For this one, it's over here. It's this rectangle. And for this one, this point gives me the minimum possible value. And for this one, it's over here. So what I'm going to do now is I'm going to add, for the lower Riemann sum, I'm going to add the areas of these rectangles up, okay? And for the last one, it's going to be this. So if you picked the the ith rectangle here, what's the area of that rectangle? It's height times the width. What's the height? Instead of max, if you start taking max of f over that interval, you're going to take its minimum. So the height of the ith rectangle is this minimum value of f over the interval xi plus 1. And then you're going to multiply this with the width, which is delta xi, and then you're going to add all these numbers up as it goes from I to n minus 1. Okay, so this is the area of the ith blue rectangle. Okay, so this is the lower Riemann sum. Now, remember what we did in 5.2? We had this disk, we had these approximations from outside and from within. Now I have my approximations from outside and from within. Just look at the picture. You can see from the picture that the area under this curve is between the area between the sum of the areas of these green rectangles, which is the upper Riemann sum, and the sum of the areas of blue rectangles, which is the lower Riemann sum. So the area under the curve is between this upper Riemann sum and lower Riemann sum. Okay, so I have my outer approximations and inner approximations. What I'm going to do next is I'm going to take the limit of these. I should explain what I mean by taking limits later. So let me write that down. So that's that. So let me put a green arrow here. Like that. Okay. So that's the upper Riemann sum, that's the lower Riemann sum. Before I proceed, maybe I should just solve an example question where I compute this. Oh, yes. Note that clearly these numbers here are less than or equal to these numbers, which means that the lower Riemann sum is less than or equal to the upper Riemann sum. Okay, so find the lower and upper Riemann sums of f of x equals x cubed over the interval 0, 1 with respect to a partition, which with respect to the partition P consisting of n equal intervals and intervals of equal length and intervals of equal length. That is, now I told you that a partition is it's just a bunch of points, two of which are the endpoints. Okay, but a partition automatically decides like if you have a partition, it automatically splits your closed interval into sub intervals. Which intervals? Well, when you take this partition, you have here have one interval here, one interval here, one interval here, one interval here, and so on. Okay. Now, sometimes instead of giving these points in the partition explicitly, people say that okay, I'm going to use the partition which consists of n equal intervals. What they like, if someone says something like this, what they mean is choose your points in the partition in such a way that the corresponding intervals are like they are of equal length, and you have blah blah many of them. So in this question, I need to consider the partition consisting of n intervals of equal length. Okay, so what I should do is I should just take this interval 0, 1, and I should just plug in my points in such a way that it's split into n intervals of equal length. So my partition P is going to be 0, 1 over n, 2 over n, 3 over n, n over n minus 1 over n, and 1. Okay, because if you just take this interval, well, I'm going to draw a picture in a second, but if you take the interval 0, 1, if you want n rectangles, if you want n intervals, and if they're supposed to be of equal length, well, the total length is 1. There are going to be n of them with equal length, so each one of them will have a length 1 over n. So the first one, the endpoint of the first one will be 0, 1 over n. The endpoint of the second one will be 1 over n, 2 over n, and so on. Okay, so this is the partition I'm talking about. So let's find the upper and lower Riemann sums for this. Let me draw actually a picture, even though this is actually not necessary. Oops. So this is how y equals x cubed looks like over the interval 0, 1. Okay? So I want to split this interval into n equal pieces. So I should have these. Okay? And then I want to write down the upper and lower Riemann sums corresponding to this partition for this function. So what I want to do is, over each interval, I need to find the point which gives me the max for each of these intervals, I over n, I plus 1 over n, I need to find the point which gives me the maximum of the function and the minimum of the function. Well, guess what? This is an increasing function. So if I take an interval of the form I over n, I plus 1 over n, the point which gives me maximum will always be the right-hand point. The point which gives me minimum will always be the left-hand point. Okay. So my rectangles, which correspond to upper and lower Riemann sums, will look like these. Green ones correspond to upper Riemann sums. Okay. It corresponds to upper Riemann sum. The blue ones correspond to the lower Riemann sum. Okay. And for this first interval, the minimum value of my function is 0. So I have a rectangle with height 0. So what's the rectangle with height 0? Its height is 0. So it's like a degenerate rectangle. It's a rectangle with height 0. Okay, there's no height, so its area is actually 0. So I'm just gonna do that, okay, to denote that its height is 0. So the upper Riemann sum for this function, which is the upper Riemann sum of this function with respect to this partition would be, so let me add the areas of the green rectangles, okay? The sum of the areas of the green rectangles. And this is equal to, what's the area of the first one? Well, the height of this is f of 1 over n. The height of the second one is f of 2 over n. The height of this third one is f of 3 over n, okay, and so on. So so this is like 1 over n, 2 over n, sorry, f of 1 over n, f of 2 over n, and f of 3 over n, f of 4 over n, and so on. So the area of the first green rectangle is f of 1 over n times this width, which is 1 over n, plus f, the area of the second green rectangle is f of 2 over n times 1 over n. This width is still 1 over n. And you're going to do this until f of n over n, which is going to be f of 1. It's going to be this point, and its width is 1 over n. So in sigma notation, what I have is I goes from 1 to n, and I have a f of I over n times 1 over n, and this is, I know what my function is. It's the cube function, so it's like f of x equals x cubed. So this is I cubed divided by n cubed times 1 over n. Okay, so this is the upper Riemann sum. And you can guess what the lower Riemann sum would be. So this is going to be the sum of the areas of the blue rectangles. So this is going to be this time the Height of the first rectangle will be f of 0 over n. Height of the second blue rectangle over here, like this is my second blue rectangle, its height would be f of 1 over n. The height of the third blue rectangle will be f of 2 over n, and so on. Okay, so this time I'm going to have the height of the first one times the width of the first one plus the height of the second one times the width of the second one. And finally, what's the height of this last blue rectangle? It is f of n minus 1 divided by n. Okay, so it's gonna go up to this point, f of like the height of the last rectangle is f of n minus 1 divided by n times its width. So you get the area of the last rectangle. And in sigma notation, this is going to be I goes from this time it's going to go from 0 to n minus 1, f of I over n, 1 over n. So it's going to be I goes from, this is not infinity, this is n. It goes from 0 to n minus 1, I cubed divided by n cubed times 1 over n. Okay, so this is the upper Riemann sum, this is the lower Riemann sum. That's fine. So the point of this question was to illustrate how you compute these upper and lower Riemann sums on an actual example. So we did that. Let's move on to the notion of integral. We haven't defined integral yet. I just computed some upper and lower Riemann sums. Now, what we want to do is we want to basically remember what we did with the disk and the polygons. We increased the number of triangles, so I get n gons, and n was increasing, and as it went to infinity, those polygons really approximated the disk. We're gonna do a similar thing. What we're gonna do is we're gonna try to increase the number of points in the partition. Okay, but like, and I want to take the limit. What does that really mean? So I'm gonna do what I described, but I'm just gonna do it like I'm gonna do something else, and the effect of what I do will be the same as taking the limit of this process as I increase the number of points in the partition, and as I make the widths of these rectangles smaller and smaller. So here's the thing. What I want to do ideally is I want to just take the limit of these Riemann sums as the number of points in my partitions increase, and the widths of these rectangles, they go to 0. I want to take the limit as these happen. What does it mean for me to take the limit of these Riemann sums as these happen? So like that's not obvious to define, because that's not like defining the limit of a function at a point. So I need to develop a certain notion of limits, which is not obvious at the moment. So instead of directly taking limits like this, I'm going to do something else, okay? Which would basically, as I said, create the same limit, same effect as taking limits. So here's what I'm going to do. I'm going to define the notion of refinement of a partition. So given partitions P and Q of AB, we say that Q is a refinement of P if P is a subset of Q. That is, every point of P is also in Q. Remember, partitions, like by definition, they are simply sets of points. I say that a partition Q is a refinement of a partition P if every point in P is already in Q. So Q presumably has more points, okay? So that's that. Observe that. So if I have a partition like this, I have these points. When I put more points, I get a refinement, okay? So observe that if Q is a refinement of P, then a then this inequality holds. Okay? Why? Let's think about this. Let's think about it. This. Let's say that you have your function, maybe something like that. Let's say that in your partition P, you have these 2 points, okay, and there's nothing in between. And you compute the upper and lower Riemann sums for P using these using these rectangles, this green one and this blue one, okay? So this is the points in your partition, and between these points, there are no other points. And if you try to compute the upper and lower Riemann sums for P, you're going to get the area of this green rectangle, and as a term, and you're going to get the area of this blue rectangle. Okay. Now, pretend that you add more points to P. It is possible that when you add more points to P, it is possible that what's going to happen is you're going to like, this need not happen all the time, but it is possible that, like, if you have a refinement, maybe you put a point in between, an extra point, okay, in between. In that case, this is going to be your I plus xi plus 1. This is going to be your xi plus 2. And let me draw the exact same function over here. So pretend that with the partition P, this is the case, and you have a refinement. Refinement means that you possibly have more points. You don't have to have more points, like in this interval, but pretend that you accidentally like you put one more point in this interval. You could have put more points, but pretend that you put one more point. What's going to happen? When you now try to compute the upper and lower Riemann sums, instead of having this area, like, remember with this partition, when you try to compute the upper Riemann sum, you had the area of that Greek rectangle. Now, if you try to compute the area, if you try to compute the upper Riemann sum for Q, you will have the area, you will have the sum of the areas of these two rectangles, and the sum of areas of these two rectangles is less than the area of this green rectangle over here. Okay, the point is, over here you are using P, over here you are using Q, and Q possibly has more points. What I'm saying is this. Ignore the second part for a second. Pretend that you have your partition, you compute the upper and lower Riemann sums. If you take a refinement of that partition, you're possibly putting more points in these intervals. But if you put more points, so let's pretend that you put one more point in this interval, what happens is, instead of considering the area of this green rectangle, you're considering the sum of areas of these green rectangles, and this sum is less than that, which means that when I add more points, the upper Riemann sum cannot increase. It can stay the same or it can decrease. And similarly, if you compute the lower Riemann sums, you are going to get a sum of areas of these blue rectangles. And the sum of areas of these blue rectangles is greater than area of this blue rectangle. Okay, so when I compute my logarithmal sum with respect to the partition P, the area of this blue one is one of my terms, but when I consider a refinement, if I have more points, then the terms, like what's going to happen is instead of having the area of this blue rectangle, I'm going to have the sum of areas of these two blue rectangles, and the sum of the areas of these guys is greater than this. So the point is, if in my partition P I have these 2 points between which there are no points, I have a certain upper and lower, like I have two rectangles here, one for upper Riemann sum, one for lower Riemann sum. And if I put more points, I will have more rectangles inside for upper and lower Riemann sums. But what's going to happen is with the new partition, the upper Riemann sum will possibly decrease. The point is it can't increase. And similarly, the lower Riemann sum cannot decrease. It may possibly increase. So if Q is a partition of P, I have this inequality, which is basically the justification of the definition that is about to come. So let's make this a bit smaller. Let's put it over here. Okay. Okay. So we say that we say that my continuous function f is integrable over AB if there exists a number I and sequences of partitions and sequences of partitions, well, a sequence of partitions and a sequence of partitions P1 subset P2 subset P3 ... and these are subsets of each other, so these guys are refining each other. If there's exists a number blah 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 such that I is equal to limit of the upper Riemann sums of F with respect to the partitions Pn, and this should be also the same as the limit of lower Riemann sums with respect to these partitions Pn. So if there is a number and there's a sequence of partitions like this, we say that F is integrable. So what's happening here is this: F is integrable if the following happens. You should be able to find a sequence of partitions such that the following happens. So I have the upper Riemann sum of F with respect to P1 over there. I have the lower Riemann sum of F with respect to P1 over here. This is always less than this because this is the lower Riemann sum, this is the upper Riemann sum. Then I get a refinement of P1. Because I have a refinement, I have that this lower Riemann sum will be greater than or equal to this, and this upper Riemann sum will be less than or equal to that. Okay. And now I have another refinement. So what I want is I want to have a sequence of partitions which are refining each other, P1, P2, P3, that's such that these upper Riemann sums, they decrease down to a number I, and these lower Riemann sums, they increase up to the same number I. If that is the case, we say that f is integrable over AB. So in this case, we say that the definite integral of f over AB is I, and write over AB is I, and write that I is equal to integral of f of x from a to b. Okay? So this is the definition of definite integral. Okay? So a couple let me write down some terminology. This is the integral sign. It just looks like those curves on a violin, and this is the upper limit of the integration, and this is the lower limit, and this function over here is called the integrand, and this x here is my dummy variable. Okay, dummy variable means that you can actually replace that x with anything else. Like, for example, if you want to use a smiley as a function, you can just integrate f of smiley with respect to smiley. Okay, x over there has no role whatsoever, so it's a dummy variable. Okay, so we now defined the definite integral. Now I'm going to write down something very important, and I'm going to talk about this. Geometrically speaking, a integral of f from a to b gives us, how do we set up the integral? We set it up in such a way that let's see. Oh, I haven't talked about this. So we said that f is integrable over blah blah if there is a sequence of partitions such that blah blah. What does this really mean? Let's think about this. We like I forgot to think about the meaning of this. If there is such a sequence of partitions, that means that you see I have like this region has some area, and from the picture you can see that the upper Riemann sum is always greater than or equal to the area, and the lower Riemann sum is always less than or equal to the area. But the upper Riemann, and this is independent of the partition, this is true for all partitions, and somehow the upper Riemann sums and lower Riemann sums, they approach to the same thing. Well, then that thing has to be the area of that region. Remember what we did in a 5.2. I approximated the disk from inside and from outside, and those approximations, like the areas of those approximations, those polygons, they had the same limit, so that had to be the area of the disk. In the same fashion, I have the area of this region under this curve. Well, the upper Riemann sums is supposed to be like greater than or equal to this for all partitions, and the lower Riemann sums is supposed to be less than or equal to this. But if my function is integrable, by definition, the upper Riemann sums approach to a number and lower Riemann sums approach to the same number. So the area of this region is squeezed in between these, but these are approaching to the same thing, and that thing has to be the area of this region. Okay, indeed, this is how we define the area of a region via integrals. Like, I'm speaking as if there is this God-given notion of area of a region, and integral gives us the area of that region. It's actually the other way around. In reality, we are defining the area of a region like this, because our construction, like pictorially, you see that if upper Riemann sums and lower Riemann sums, they converge to the same number, that number ought to be the area of that region. Okay, so geometrically speaking, blah blah gives us the, now I'm going to do something, signed area of the region between y equals f of x and the x-axis over the interval AB. Okay. Okay, so this is important. Remember I told you that our motivation is to compute the area of the region under the graph of which is like our motivation is to compute the area of a region, which is the region under the graph of a curve over an interval, blah blah. It's the first question that I wrote, but I kind of like I said that like, okay, this does what I hoped it would do, but I kind of lied. Here's the thing: when I said this is the height of the rectangle, this term is the like over here. I said that this is the height of the rectangle. Well, what if my function has negative values? In that case, it's not the height. It's like the negative of the height. Because if this picture were below the x-axis, if my function took negative values, this f of x would not be the height, it would be the negative of the height, okay? So instead of computing the area of this rectangle, I would be computing negative of the area of that rectangle, okay? So let me come up with a different concept. Let me define the concept of signed area of a region. What do I mean by signed area? Signed area means this, like you have a region in the plane. Signed area of this region means this. If this region is above the x-axis, you count, you pretend that the area is of the parts of this region above the x-axis has positive area, and the parts below has negative area, whatever that means. Okay, so I'm counting the stuff above x-axis as positive, and I'm counting the stuff below x-axis as negative. And signed area means that you treat the parts of this region below the x-axis as if they have negative area. You treat the other ones as usual. And then signed area means that compute the total area under these assumptions. Okay, so what that means is, for example, pretend that this is 1, 1, 2, 1. The signed area of this region would be 0. The reason is these squares are exactly the same. They have a area 1, but because I'm interested in signed area, I count this as having signed area plus 1, and I count this as having signed area minus 1 because it's below the x-axis. Okay. Now, with this like after this definition, which I didn't write down, like if I define what it means, like if I define the signed area properly, you can actually get that what we defined here, this notion of definite integral, should not give us the area of a region. It should not give us the area of the region under a curve over an interval. It should give us the signed area, because whenever my function is negative, the corresponding rectangle here will have a, like, if my function takes negative values, and if the max or min is attained by that negative value, then the corresponding rectangle will be, it will stay below the x-axis, meaning that it's like if I'm computing the signed area, its area should be counted as negative, but this exactly does that. Like if my function takes negative values, this term will already be negative. Okay, so what this term really computes is not the area, like I said, it's the area of the blue, it's the area of the light blue triangle. In reality, it's actually the signed area, okay, of the light blue triangle. Okay, so I have that. So this is the geometric interpretation of definite integral. Now, many of you learned like you were told that the integral is the inverse operation of derivative. Well, that's simply, at least, well, that's true. That will be true after we prove the fundamental theorem of calculus. That's actually even false. Integral is not the inverse of differentiation. Integral has a definite meaning. It's the limit of certain upper and lower Riemann sums. Okay. It has a geometric meaning. It gives you the signed area. It can be computed via antiderivatives, and the operation of taking antiderivatives is literally the inverse of taking derivatives. It can be computed via antiderivatives, but that is the fundamental, that relation, that's not something obvious. That is the fundamental theorem of calculus. So the point is, many of you think that integral by definition is the inverse of the integration is by definition the inverse of differentiation. Well, if by integration you mean computing definite integrals, no. Definite integral by definition is a certain limit of Riemann sums. Okay. Now, here's a fact that I am not going to prove. Okay. Fact, or maybe I should say theorem. Okay, I define what it means for a function to be integrable, but with which functions are integrable. If f is continuous over AB, then f is integrable over AB. Okay? So, I made a definition here. I said that f is integral if blah blah happens, but it's not obvious that that blah blah can actually happen. Like, making definitions, like everyone is free to make definitions. I can define a pen to be like, I don't know, integrable. I'm saying that a pen is integrable if this pen is equivalent to a flying elephant. Okay, here's the definition. I say a pen is integrable if this is a flying elephant. Well, then there are no integrable pens because there are no flying elephants. Just because I made a definition doesn't mean that there are such objects. Okay, it doesn't mean that the adjective actually makes sense. But it turns out that I do have integrable functions, and indeed, if you have a continuous function on a closed and bounded interval, it is integrable. Okay. The proof of this is beyond the scope of this course. It requires for you to know the notion of uniform continuity. Okay, uniform continuity is basically about, remember the epsilon delta definition of continuity. For each point and each epsilon, there's a delta blah blah. Uniform continuity means that that delta is independent of your point, and continuous functions over closed and bounded intervals are uniformly continuous. So using some tricks, you can actually show that if you have a continuous function over a closed and bounded interval, when I give you an epsilon, you can find me a very, very tiny delta, so that if you choose your partition in such a way that the largest width of the rectangle is less than delta, the difference between upper and lower Riemann sum would be less than your given epsilon. You can actually show that using the definition of uniform continuity, which you don't know, and this can be done. So the point is, it's not that difficult to prove this, but I have to teach you about the notion of uniform continuity, which is not included in this course, so we're going to skip the proof of this non-trivial fact. Okay, so that's that. Now, before solving some examples, let me talk about general Riemann sums. General Riemann sums, okay? So, while constructing the upper and lower Riemann sums, if one uses an arbitrary point, an arbitrary and a arbitrary sample point a xi star in the interval xi plus 1 a instead of the points which make f attain its maximum and minimum values. Then one can define, if one uses blah blah, one can define general Riemann sums. Okay, general Riemann. Okay, Riemann sums. So what I'm going to do is, instead of in the definition of upper and lower Riemann sum, you see over here, I said that you take the maximum of f. So you take the point which gives you the largest possible value of f over that interval, whatever it is. Over here, you use the point which gives you the lowest possible value. Now, instead of the points which give me the maximum and minimum of f, maybe I should just take some arbitrary point. What happens? In that case, you get these arbitrary Riemann sums, okay? So I'm going to denote them like this. So Riemann sum of f with respect to partition P with sample points x1 star, x2 star, dot, dot, dot is, you're going to do the exact same thing, okay? Like, you're going to have the exact same thing here, except instead of this max, you're going to use the value of a value of your function at the corresponding sample point. So you're going to have xi star here and delta xi. Okay, so what this is going to do is this. Let's say that this is your interval xi plus 1, and let's pretend that this is your function. Now, for upper Riemann sum, you use the point which gives you the largest possible value. For lower Riemann sum, you're going to use the point which gives the minimum the least possible value, the minimum value. For a general Riemann sum, you're free to use any point that you want. You fix sample points ahead of time. So I'm just going to pick some arbitrary point. Let's say that xi star here. And then I'm going to use the value of the function at this point to determine the height of my rectangle. Okay, so I am going to have this rectangle. Okay, so instead of having these green and blue rectangles as in upper Riemann sums and lower Riemann sums, I'm just going to have these white rectangle whose height is determined by a point that I chose. So I fix some sample points and I do that. So this, like, you can define general Riemann sums like this. Okay, clearly, this is going to be less than or equal to the upper, this is going to be greater than or equal to the lower Riemann sums, and this is going to be less than or equal to the corresponding upper Riemann sums, okay? Because in each interval, instead of the point which gives you the maximum value and the minimum value, you're using an arbitrary value. But the height of the rectangle determined by the arbitrary value cannot be greater than the height which you observe, which you get in the upper Riemann sum, and it can't be less than the height which you get in the lower Riemann sum. So we have that. Okay, that's that. One more fact, which I'm not going to prove, but we're going to use this in a question in about 5 minutes. Fact: if f is integrable over an interval AB, then the integral of f over AB is, okay, the limit of a a these general Riemann sums for all choices of sample points, and you're taking the limit of these Riemann sums for all choices of sample points as as where MP denotes a the number of points in P, and delta P denotes the length of, well, it denotes the maximum of a delta xi, as I is between 1 and MP. So let me go over this. If you have an integrable function, the integral can be actually computed as follows. You take a partition, you take a general Riemann sum with whatever sample points you want to use, you compute your Riemann sum. Now do the following. Increase the number of points in your partition and increase them in such a way that the maximum delta x, you see we have delta x's here, the maximum delta x gets smaller. Okay, compute another Riemann sum. Keep doing that. You're going to get numbers, and take the limit of these numbers as the number of points in your partition goes to infinity, and the maximum delta x goes to 0. Okay, so you're supposed to take the limit of Riemann sums as the maximum delta x goes to 0 and the number of points in your partition goes to infinity. If your function is integrable, then this limit will be the same as the integral. Okay, so instead of defining integral in terms of upper and lower Riemann sums, I could have defined it like this, but then I had to talk about general Riemann sums, and I think this is more complicated. But this fact is true, and we're not going to prove this. So this says that if you know that your function is integrable, you can find that integral by taking limit of a certain general Riemann sums, where the number of points in your partitions over which you're taking limit goes to 0, and the number of their maximum delta x's go to 0. So the number of points in the okay. I'm sorry, I got tired. I think it's been over an hour, right? Maybe more than that. So this is what it is. Now let me solve 2 questions. Let's actually compute an integral. Example: find the integral of x cubed from 0 to 1 using the definition of the definite integral. definite integral. Okay. Solution. Where is it? So we computed the upper and lower Riemann sums. Okay. For this partition, let me name this partition Pn. Okay. Pn. Let me name this Pn. Recall that we computed the upper and lower Riemann sums of f of x equals x cubed with respect to the partition Pn, which is this n over n before. Okay, taking the limits of these, we get that. Now let me take the limit of the lower Riemann sums of this function of x equals x cubed with respect to Pn. What was this? We computed this before. It was over here, lower Riemann sum. It's over here. So I cubed divided by n to the power 4. Okay, this is like cubed. I cubed divided by n to the power from 0 to n minus 1. So I goes from 0 to n minus 1. I cubed divided by n to the power 4. Now, I can put this n outside sigma because this doesn't involve any I, and in this sum was changing as I, so I can put this n to the power 4 outside. This is like a constant from the point of view of this summation. Okay, now a formula, which I'm gonna write down in a second, tells me that if I add the cubes of numbers from 0 to, let's say, k, then that sum is k plus 1 divided by 2 squared, okay? So I get that this is a n minus 1 and divided by 2 squared. Why? Because like this is a well-known formula which I'm not going to prove. If you add the cubes of numbers from 0 to k, then you're going to get k plus 1 divided by 2 squared. Okay, and this turns out to be the limit of these lower Riemann sums. Now you can get this limit as 1 over 4. Okay, like, you know how to compute limits. At this point, I'm not just going to open up and say that, okay, you get a 4th-degree polynomial at the top, you get a 4th-degree polynomial at the bottom. You're taking the limit of this at infinity. So what do? You look at the leading coefficients. Leading coefficient at the top is 1, leading coefficient at the bottom is 4, so the limit is 1 over 4. I'm not going to write that down. I just said it in words, okay? And let's compute the limit of the upper Riemann sums. Now this is, where is it? It's the sum of I cubed over n to the power 4 as n goes from 1 to n this time. So this is going to be, I'm putting this into I'm pulling this 1 over n to the power 4 out, and I have this and 1 over n to the power 4. From this formula, I am going to get n plus 1 squared divided n plus 1 divided by 2 squared, and this is going to be 1 over 4 as well. Okay, so I get 1 over 4. Now, what have I obtained? I have a sequence of partitions, okay, these are not refining each other, but that's fine. I'm going to explain that. Okay, what have I obtained? I obtained a sequence of partitions for which upper Riemann sums and lower Riemann sums approach to the same number. Now, using these partitions, you can actually get partitions which are refining each other so that this will happen, like they will approach to the same limit. How? Basically, start with the first one, and then the second one is not refining the first one. So what you're going to do is you're going to take simply the first one union the second one. So you're going to combine the points in this. So this will be a refinement of this, and it's going to be less than that. And then you're going to add the third one to this. So you're going to add the points in the third one to this. So you're going to get a refinement of the previous one. So this is going to be less than that. Okay. And by definition, you know that like if you keep doing this, they're going to decrease like this. And each of these guys are less than it, like this one is less than or equal to UFP2, this one is less than or equal to UFP3, and so on. Now, the limit of UFP1, UFP2, UFP3, this is 1 over 4, which means that the limit of this sequence has to be 1 over 4 as well, okay? Why? Because, you see, over here, which I didn't write down the lower Riemann sums, but over here I have the lower Riemann sums as well, like this, f of P1. This is greater than or equal to f of P1 union P2. So I add the points in P1 and P2 together. And this is going to be greater than or equal to L of P2 and so on. Now, imagine the symmetric picture, which I'm not writing down. These lower Riemann sums increase up to 1 over 4. These decrease down to 1 over 4. So what's going to happen is the integral of this function will be 1 over 4. Okay? So let me erase all this. So because we have a sequence of partitions, a Pn, such that the limit of upper Riemann sums and the limit of lower Riemann sums with respect to these partitions, because these limits are both 1 over 4, we have that the integral of x cubed from 0 to 1 is 1 over 4. Okay. Now, you may object at this point that, okay, in the definition of integrability, you assume that these partitions are refining each other. Well, it can actually, that condition can actually be dropped. Okay, so let me write that down. So let me write that down over here. That these PNs refine each other is actually not necessary. Okay? Okay. Why am I squeezing it over here? Maybe I should just write that down. The point is, in this definition, I took this as as a part of the definition. I said that these partitions should refine each other. That part actually, like, you can actually drop that condition. If you drop that, if you simply say that you have a sequence of partitions such that blah blah happens, that definition is equivalent to this definition. Okay. So let me write that down. A fact that P1 should be listener A is subset of P2, should be a subset of P3, in the definition of integrability can actually be dropped because if you can find a sequence of partitions for which these upper Riemann sums and lower Riemann sums approach the same thing, if you can find a sequence of partitions which are not necessarily refining each other, like if you can find a sequence of partitions where these numbers approach to the same thing and you don't assume that these are refining each other, what you can do is you can always like instead of P2 you can replace this with P1 union P2, okay, and you can make this even smaller than before. Like if P2 is not refining P1, then they have a common refinement, meaning that I have a third partition which refines both, namely P1 union P2. So by replacing this with P1 union P2, you can turn any such sequence of partitions into a sequence of partitions like this, which refine each other and for which you have that the upper Riemann sums and lower Riemann sums approach the same thing. Anyway, so that's that. Okay, I'm gonna solve one more question and stop the lecture. I don't know what time is it right now, but I'm getting like, I'm afraid that it might be close to 2 hours. We'll see when I stop this video. So over here, what we did is we computed the upper and lower Riemann sums for a fx equals x cubed over the interval 0 on before for a sequence of partitions. I took the limit of these upper and lower Riemann sums. I got 1 over 4. So now I have a sequence of partitions over for which the limit of upper Riemann sums and limit of lower Riemann sums, they approach to the same number. That number has to be the integral of this function, which is the case. It's 1 over 4. Now, all of you learned how to compute integrals in high school, and you computed this directly as well. This is x to the power 4 divided by 4 from 0 to 1. It's 1 over 4. So I already knew that. Why did he do this? Well, because this fact is the fundamental term of calculus, and it's not obvious. It's not something that comes for free. We have to work for that, okay? So over here, I computed this integral using the definition. And as you can see, even for such a simple integral, using computing this integral with the definition requires a lot, taking a lot of limits, and requires us to compute a lot of Riemann sums. So the point is, even though the definition of definite integral that we covered today, it makes perfect sense geometrically, like it gives me the signed area, it's not practical for computation purposes, which is why we have to come up with other ways to compute definite integrals, which is going to bring us to the notion of fundamental term of calculus later in 2 sections, I guess. So let me solve one more question, and then we're going to stop. Example: find the limit of okay. So I'm taking the limit of a certain sum. Sum of what? Sum of square root of n squared minus I squared divided by n squared as I goes from 1 to n. Okay? So this is like, let me write this down explicitly without sigma notation. It's like for I equals 1, I get n squared minus 1 squared divided by n squared plus, then I have n squared minus 2 squared divided by n squared plus dot. Then I have n squared minus 1 squared divided by n squared plus n squared minus n squared divided by n squared. So for each n, I compute this finite sum and then I take the limit. What is this limit? Now, what I'm going to do is, like, in practice, no, you won't run into, okay, let's be honest, in practice, you won't run into such a, in practice, you won't run into such a problems, okay? What's going to happen is, like, why am I solving this question? To teach you about Riemann sums. So in practice, you're not going to run into such questions because no one would ask you, like, compute this limit. Like, it looks so made up, and it is made up. This question is specifically made up for you to understand Riemann sums. What we're going to do is we're going to see this sum as a Riemann sum, and then taking the limit of this Riemann sums would correspond to computing the definite integral, okay? Okay, so here's what I'm going to do. I am going to rewrite this as follows. I'm just going to write, instead of 1 over n squared, I'm going to write 1 over n squared minus I squared. Why? Remember, when I used a partition with a, when I used a partition with a intervals of equal length, my delta x turned out to be 1 over n all the time. So my approach to this question is, okay, like, I'm going to try to see this as a Riemann sum, but in order for me to be, like, in order for me to do that, I need to first, like, fix an interval, fix some delta x and so on. And delta xi need not be a same number. It may, like, delta xi need not be a fixed number. It may depend on I. But for this example, for this specific example, I'm going to pretend that I'm using a intervals of equal length, so these delta xi's are all the same. Okay, where is it? Yes. So I'm gonna see this as my delta xi, and I'm gonna try to think of some function f so that this will be my f of a xi star, where xi star is the sample point that I'm using. So I'm trying to see this as a general Riemann sum. Okay, so let me play with this more. So let me put this a n inside square root as n squared, so that I get a 1 minus I squared over n squared. Now this is exactly, oh, I forgot my sigma. Okay, now this is exactly the Riemann sum. This is actually exactly the lower Riemann sum of the function f corresponding to the partition Pn where f of x is square root 1 minus x squared and a Pn is this partition of 0, 1. Okay, so if you have this function y equals square root 1 minus x squared, and if you compute these lower like if you split this interval into n pieces, and this is like n over n, and if you try to compute the lower Riemann sums, because it's a decreasing function, you will be using these right hand points. Okay, so these will be your rectangles and so on. If you compute the area of this ith rectangle, it will be like pretend that this is I over n. Well, sorry, pretend that this is I over n, a right hand point. So this will be, the area of this will be a 1 over n times, the area is 1 over n times square root 1 minus, well, I squared divided by n squared. Okay, and you're changing I from 1 to n. Okay, so this is my last, never mind, I'm not gonna draw that. So for I equals 1, you get the area of this. For I equals 2, you get the area of that, and so on. So for the rectangle where this right-hand point is I over n, the area will be 1 over n times square root 1 minus I squared divided by n squared. So you get this term. So you see that this is the lower Riemann sum for this function. As a f is integrable over the interval 0, 1, we get that. Now, we get that this limit is which is the limit of these lower Riemann sums. You see, the number of points in these partitions go up to infinity, the maximum width go to 0. So by this fact, which I listed over here, I see that this is actually the integral of square root 1 minus x squared from 0 to 1, but this is equal to, remember the geometric interpretation, it's supposed to be the signed area of the region under this curve, so this is equal to the area, the quarter of the area of the unit disk. You see, this is a part of, this is like the 1/4 of the disk. X squared plus y squared is less than or equal to 1. So if I were to draw x squared plus y squared equals 1, I would get a circle, and this is like 1/4 of the circle. So the area under this curve would be the quarter of the area of a unit disk, and that is, remember, we now know how to compute, well, you already knew how to compute the area of a disk, but we actually proved that, we actually derived that formula. So the area of the unit disk is pi, so its quarter is pi over 4. So this limit is actually pi over 4. So what did I do here? I'm given this interesting limit of a certain sum, and then I tried to see the sum as a Riemann sum, and it turned out to be a lower I could have seen this as a general Riemann sum for some other function as well, but I realized that I can see this as a lower Riemann sum for the function square root 1 minus x squared for a partition where I have n intervals of equal length, and then by this fact, if I compute a limit of general Riemann sums where the number of points go to infinity and the maximum width goes to 0, if I take the limit of such Riemann sums, that limit has to be the integral of the function, provided that my function is integrable. But this function is integrable, and this is such a sequence of partitions where the number of points go to infinity and the largest width goes to 0. So this limit is equal to the integral of this function, which by the geometric interpretation of the integral is equal to the area of the region under the curve. But that's just like a quarter disk, which has area, it's a quarter unit disk, which has area pi over 4. Okay? So this, you're gonna solve more questions like this in your recitation, and you're gonna, I guess, solve a couple, maybe 2 questions like this where you compute a definite integral using Riemann sums. So I think like 3 questions for this lecture should be enough. This section is like by nature we were supposed to do more theory than practice in this section, and that's what we did. Like I only solved 3 questions, but we did a lot of theory, and that's that. So wait for the recitation videos and stay safe.